Here's something that should keep you awake tonight. In December 2025, scientists found ribose on an asteroid. Ribose, the sugar backbone of RNA, the molecule that probably started all of this, sitting on a rock that's been dead for 4.5 billion years. That alone rewrites the textbooks. But here's what nobody's telling you. While everyone panicked about that discovery, another object, 3I Atlas, quietly entered our solar system and started manufacturing those exact same molecules in real time. Not preserving them, producing them. And in March 2026, Earth passes directly through its wake. Stay with me until the end, because what we're about to discuss isn't just about finding life's building blocks. It's about watching the delivery system activate. If you're as captivated by these revelations as I am, go ahead and like this video and subscribe so you catch every development as this story continues to unfold. Leave a comment telling me where you're watching from, what hour of the night it is, and what you think about this new development. Part 1. The double discovery nobody expected. You're about to hear something that will rewrite how we think about life in the universe, and it starts with a small canister that travelled 2.7 billion kilometres to get back to Earth. On September 24th, 2023, a capsule the size of a mini-fridge dropped out of the sky over the Utah desert. Inside that capsule was 250 grams of material from an asteroid called Bennu. Scientists spent 2 years analysing every molecule, and in December 2025 they published results that nobody was prepared for. They found ribose, they found glucose, they found 33 amino acids, 14 of which are essential to every living thing on this planet, and they found nucleotides, the literal building blocks of DNA and RNA, sitting inside a rock that has been floating through space for 4.5 billion years. Now you might be thinking, okay, organic molecules on an asteroid, we've seen that before. But here's the thing. Ribose is what scientists call the holy grail molecule. It's the sugar backbone of RNA, the molecule that probably came before DNA, the one that might have sparked the whole show we call life. And ribose is notoriously fragile. Cosmic radiation shreds it. Ultraviolet light dismantles it. Heat destroys it. Finding intact ribose on Bennu is like finding a snowflake in a blast furnace. It shouldn't be there, yet there it is, confirmed, verified, sitting in a lab in Houston right now. The amino acid count is even more baffling. 33 different types. Most carbonaceous meteorites that fall to Earth contain maybe 10 or 15. Bennu has more than twice that, and the ratios, the proportions of left-handed versus right-handed molecules, they match the chemistry of prebiotic Earth more closely than any sample we've ever analysed. The nucleotides are the knockout punch. DNA and RNA building blocks don't just casually form in space. They require specific conditions, catalysts, energy, protection from radiation. Bennu somehow became a vault for the ingredients of life, a time capsule sealed 4 billion years ago. But here's where it gets strange. While scientists were analysing Bennu's ancient molecules, another object was entering our solar system. Its name is 3I Atlas, and it's not acting like a normal comet. On September 5th, 2025, when Atlas was still 2.5 astronomical units from the Sun, it started glowing. Not the typical comet brightening you'd expect from ice sublimating. This was different. The brightness doubled in 48 hours, then kept climbing. Spectroscopes aimed at Atlas detected something nobody anticipated. Organic compounds, carbon chains, molecules that match the chemistry found in Bennu's samples, but with one critical difference. These weren't ancient residues. The spectral signatures suggested active synthesis, fresh production. Scientists started, calling Bennu the archive and Atlas the factory. One object preserved the ingredients of life for billions of years. The other appears to be manufacturing those same ingredients right now, in real time, as it barrels toward the Sun. If you're looking for a cosmic smoking gun, this is it. We have the evidence of what's possible, frozen in Bennu's rocks, and we have the mechanism playing out in front of every telescope on Earth, embedded in Atlas's glowing tail. Now, the conservative explanation is that Atlas is just a very unusual comet, a chemically rich interstellar visitor that happens to contain similar organics. Comets can do weird things. They outgaze, they crack, they brighten unpredictably. But the timing here is too clean, the chemistry too precise. Atlas didn't just wake up randomly, it activated at exactly 2.5 astronomical units from the Sun, the distance where solar flux jumps high enough to melt subsurface ice and trigger liquid water pockets. And here's the kicker: liquid water at 2.5 AU is unusual. It requires either incredible insulation or some form of internal energy storage. Atlas seems to have both. The term floating around in private scientific meetings is global phase transition event. That's a fancy way of saying the entire object changed state, not just one vent popping open. Rotation data supports this. Atlas spins every 16.6 hours, and the heating signatures are homogeneous, meaning the whole surface is participating in whatever process is happening inside. Thermal models suggest that when the ice melted, it didn't just create random pockets. It formed interconnected reservoirs, possibly a subsurface ocean, where water could circulate and interact with the rocky metallic core. And that's where things get chemical. Atlas is loaded with iron and nickel, the same metals that act as catalysts in a process called Fischer-Tropsch synthesis. You take carbon monoxide or carbon dioxide, add hydrogen from water, introduce a metal catalyst, apply heat, and you get organic molecules, amino acids, sugars, alcohols, the same compounds Bennu preserved, the same compounds Atlas is now producing. If Bennu is the evidence that this process happened in the ancient solar system, then Atlas is the live demonstration, the engine running in real time, showing us exactly how it works. But why now? Why did Atlas remain inert for 10 million years of interstellar travel, passing other stars, other systems, only to wake up when it entered our solar system? Sunlight alone doesn't explain it. Plenty of comets pass through the same region without triggering this kind of reaction. Some scientists are quietly asking a question that makes everyone uncomfortable. What if Atlas was designed to activate only within a certain range of stellar radiation? What if the chemistry we're seeing isn't accidental but optimized? What if we're not watching a comet? What if we're watching something that was sent? And here's the part that should keep you awake at night. In March 2026, Earth is going to pass directly through the position where Atlas reached perihelion. If Atlas is ejecting organic material into stable orbits, and if that material survives long enough, then we're about to walk through a cloud of biologically active molecules from an interstellar object. We've never done that before. We don't know what happens next, but we're about to find out. Part 2, the activation event at 2.5 AU, what the teams aren't saying publicly. Let's rewind to September 5th, 2025. Atlas is still 2.5 astronomical units from the Sun, roughly 375 million kilometers out, just past the orbit of Mars. Most comets at this distance are dark, dormant, waiting for the Sun's heat to reach them. But on that day, telescopes monitoring Atlas recorded something unusual. The brightness spiked, not gradually, not over weeks. In less than 48 hours, Atlas doubled in luminosity, and then it kept going. By September 7th, it was 3 times brighter than projections predicted. Observatories scrambled to retask instruments. Something was happening that didn't fit the models. Comet outbursts aren't rare. Subsurface ice pockets can rupture, releasing jets of gas and dust that temporarily brighten a comet before fading again. The key word is temporarily. Outbursts spike and drop. They're localized events, usually triggered by a crack in the surface or a sudden exposure of volatile material. But Atlas didn't spike and fade, it spiked and accelerated. The brightening continued all the way to perihelion in late November, intensifying as it approached the Sun. That's not how outbursts work, that's how phase transitions work. At 2.5 AU, the solar flux reaching Atlas increases just enough to push subsurface temperatures above the melting point of water ice. If Atlas has significant internal insulation, maybe layers of rock and dust mixed with the ice, then that heat doesn't dissipate quickly. It accumulates. Ice melts. Liquid water forms. And once you have liquid water inside a body loaded with carbon, metals, and organic precursors, chemistry accelerates exponentially. Reactions that take millions of years in frozen conditions happen in days when water is present. The term some scientists are using in internal discussions is global phase transition event. Not a localized crack, not one vent opening, the entire object changing state. How do we know it was global? Rotation data. Atlas spins every 16.6 hours, and thermal imaging shows homogeneous heating across the surface. If only one side was active, we'd see temperature asymmetries. We don't. The whole object is participating. Spectroscopic analysis shows emissions coming from multiple angles. Not just one jet or plume. Whatever process activated Atlas, it engaged the entire body simultaneously. That requires either incredible internal connectivity or a uniform distribution of reactive materials throughout the object. Either way, it's not random. Now, here's where the chemistry gets interesting. Atlas has a carbon dioxide to water ratio of 8:1. That's wildly unusual. Most comets have ratios closer to 1:1 or even water dominant. An 8:1 ratio suggests constant oxidation cycles, likely driven by interactions between water and metallic elements in the core. When water contacts iron or nickel at elevated temperatures, it produces hydrogen gas and metal oxides, primarily magnetite. Hydrogen is the key ingredient for Fischer-Tropsch synthesis. Add carbon monoxide or carbon dioxide, introduce the metal catalyst, apply heat, and you start producing organic molecules. Atlas isn't just outgassing, it's reacting. The melting event at 2.5 AU didn't just release frozen volatiles. It initiated a catalytic process that's been dormant for millions of years. Think of it like striking a match. The heat provides the activation energy, but the fuel was always there, waiting. Once the reaction starts, it becomes self-sustaining as long as the conditions remain favourable. Solar heating maintains the temperature, water circulation distributes reactants, metal catalysts remain active, the factory is online. But here's the coincidence problem. Why did the activation align so perfectly with the solar flux threshold? Comets come in all compositions. Some activate early, some activate late, some barely activate at all. Atlas activated at precisely the distance where liquid water becomes possible, but not so close that thermal stress would fragment the object. It's like the chemistry was tuned to a specific energy range. Natural processes can produce narrow activation windows, but they're usually messy, inconsistent. Atlas's activation was clean, predictable, almost engineered. Some scientists are privately speculating, and I want to be clear this is speculation, that Atlas might be designed to wake only when it enters a habitable zone flux environment. Not because someone programmed it with computer chips, but because the chemistry itself is optimized for that exact energy threshold. If you wanted to distribute organic precursors to potentially habitable planets, you'd want your delivery system to activate only when it reaches the right conditions. Too early, and the molecules degrade before arriving. Too late, and you miss the target. 2.5 AU is the Goldilocks distance, enough heat to start the reactions. Not so much that the object disintegrates. Is that what's happening? We don't know. What we do know is that Atlas didn't behave randomly. It responded to a specific environmental trigger with a coordinated, sustained reaction. The brightening wasn't chaotic. The chemistry wasn't accidental. Something about crossing that threshold at 2.5 AU flipped a switch, and the entire object transitioned from dormant to active in less than 72 hours. That's not typical comet behaviour, that's something else. And then there's the jet, the one pointing toward the sun, the one that shouldn't exist. Because comets don't do that. Comet tails point away from the sun, pushed by solar wind and radiation pressure. Jets can form at angles, sure, but a persistent growing plume aimed directly at the sun? That's physically contradictory unless something is overriding the normal physics. Unless there's a magnetic field, unless there's plasma shaping, unless Atlas isn't just a comet. We'll get to that. But first, you need to understand why finding liquid water at 2.5 AU matters. Because liquid water doesn't just enable chemistry, it enables complexity. And complexity is how you get from simple molecules to the building blocks of life. Atlas crossed that line on September 5th, and it hasn't looked back since. Part 3. The sunward jet, the tail that shouldn't exist. On December the 1st, 2025, astronomers imaging Atlas noticed something that made them double-check their instruments. A bright plume was growing from the comet's nucleus, but it wasn't pointing away from the sun. It was pointing toward it. If you know anything about comets, you know that's wrong. Comet tails are pushed by solar wind and radiation pressure, always pointing away from the sun like hair in a breeze. Jets can angle in different directions depending on where they vent from the surface, but they still follow the overall pattern, anti-sunward, always. Except Atlas decided to ignore that rule. The sunward jet is real. Multiple observatories have confirmed it. It's not an instrument error. It's not a perspective illusion. There's a growing luminous plume of material streaming from Atlas toward the Sun, defying the basic physics that govern every other comet we've ever studied. The question is why, and the answers get progressively stranger the deeper you look. One possibility is magnetic deflection. If Atlas has a strong localized magnetic field, it could interact with the solar wind in ways that shape plasma jets. We've seen hints of this before with Comet 67P Churyumov-Gerasimenko. The Rosetta mission detected magnetic field spikes up to 300 nanoteslas near the nucleus, strong enough to deflect charged particles and create small-scale plasma structures. But 300 nanoteslas is weak on a cosmic scale. It can nudge particles, but it can't reverse the direction of an entire jet against solar wind pressure. For that, you'd need a much stronger field, orders of magnitude stronger. Here's where the magnetite comes in. Magnetite is iron oxide, and it's magnetic. When water reacts with iron and nickel inside Atlas, one of the primary byproducts is magnetite. If the interior is actively producing magnetite through ongoing water-metal reactions, and if those magnetite crystals are accumulating in specific regions, you could, theoretically, build up a significant magnetic field over time, not strong enough to deflect the entire solar wind, but strong enough to create a localized magnetosphere around the nucleus. A magnetosphere is essentially a bubble of magnetic influence. Earth has one, Jupiter has one. Even some asteroids have remnant magnetism from ancient core activity. If Atlas has an active magnetosphere, it could channel plasma along magnetic field lines, creating jets that don't follow the normal solar wind flow. Think of it like a nozzle on a hose. The pressure still pushes water out, but the nozzle directs where it goes. Atlas's magnetic field could be directing plasma toward the Sun, not because it's fighting against physics, but because it's using a different set of rules. But that raises another question. Why would a magnetosphere form in the first place? Magnetite production is one thing. Organizing it into a coherent field structure is another. On Earth, our magnetic field is generated by a dynamo effect in the molten outer core. Convection currents in liquid iron create moving electric charges, which generate magnetic fields. Atlas doesn't have a molten core in the traditional sense, but it might have something functionally similar. A rotating body with liquid water circulating through a metallic matrix could theoretically produce weak dynamo currents, especially if the rotation homogenizes the internal flow. 16.6-hour rotation isn't fast, but it's consistent, and consistency matters for magnetic field generation. If Atlas is generating its own magnetosphere, even a weak one, the implications are staggering. It means the object isn't just passively outgassing, it's actively interacting with the solar environment in ways that require internal structure and energy flow. A magnetosphere requires current. Current requires movement. Movement requires energy. Where is that energy coming from? Solar heating can explain surface activity, but generating and maintaining a magnetic field implies deeper processes, possibly chemical energy released from ongoing Fischer-Tropsch reactions, or latent heat stored in the melting ice. Now, here's where it gets speculative, and I want to flag this clearly. If Atlas has a magnetosphere, and if that magnetosphere is shaping the outgassing into directed jets, then the sunward plume might not be random. It could be aligned with the ecliptic plane, the flat disk where Earth and the other planets orbit. Why does that matter? Because ejected material that stays within the ecliptic has a much higher chance of intersecting planetary orbits. If you wanted to distribute organic molecules to planets, you'd want your ejection stream to align with where the planets are. You wouldn't spray material in random directions, you'd aim. Is Atlas aiming? We don't know. What we do know is that the sunward jet is persistent, growing, and aligned in a way that maximizes the probability of Earth intersecting its wake in March 2026. Earth's orbit crosses the exact position where Atlas reached perihelion. If material from that jet remains in stable orbits, which some simulations suggest it could, then we're flying through it whether we want to or not. Not a collision. Not an impact. Just a passage through a cloud of organic-rich particles ejected from an interstellar object that's behaving like nothing we've seen before. Some scientists are calling it a biological ejector delivery stream. That's not sensationalism. That's a description of what's physically happening. Atlas is ejecting organic molecules at high velocity into orbits that intersect Earth's path. Whether those molecules survive re-entry, whether they could seed anything, whether they even reach the surface, those are open questions. But the geometry is undeniable. We're walking into it. And the fact that the jet is pointing toward the sun, the fact that it's aligned with the ecliptic, the fact that Earth happens to pass through that exact region at that exact time, it's either the most extraordinary coincidence in astronomical history, or it's something else entirely. Something that makes people uncomfortable to even consider. But we're past the point of comfort now. We're in the realm of evidence, and the evidence says Atlas isn't behaving like a comet. It's behaving like a delivery system. Part 4. The Bennu-Atlas Chemical Paradox. Let's talk about something that shouldn't be possible. Bennu samples contain ribose, glucose, and 33 amino acids, molecules that cosmic radiation should have destroyed millions of years ago. Ribose in particular has a half-life in space measured in thousands of years under typical radiation exposure. Bennu is 4.5 billion years old. That's 4 million times longer than ribose should survive. Yet there it is, intact, preserved, sitting in a sample container in Houston. How? The answer is shielding, magnetite shells. When scientists analysed the Bennu samples under electron microscopes, they found organic compounds encased in thin layers of magnetite, iron oxide crystals that form when water oxidizes metallic iron. Magnetite is magnetic, dense, and crucially, it blocks cosmic radiation. Think of it like lead shielding around a nuclear reactor. The organics inside the magnetite shells were protected from the relentless bombardment of high-energy particles that permeate space. Without that shielding, they would have degraded into simpler compounds long ago. But the magnetite preserved them, locking them in a state of chemical stasis for billions of years. Now here's where it connects to Atlas. The spectral data from Atlas shows active magnetite formation happening right now. The 8:1 carbon dioxide to water ratio indicates ongoing oxidation reactions. Water is reacting with the metallic core, producing hydrogen gas and magnetite crystals. The same process that preserved organics in Bennu is currently happening inside Atlas. Except Atlas isn't preserving ancient molecules. It's producing new ones, coating them in magnetite as they form, creating a fresh batch of radiation-shielded organic compounds ready for ejection into space. The spectral overlap between Atlas and Bennu is unsettling. Outgassing from Atlas matches the amino acid and sugar ratios found in Bennu's samples more closely than any known comet or meteorite. It's not identical, but it's close enough that several research groups have privately noted the correlation. One scientist described it as fingerprinting. If you analyse a crime scene and find DNA that matches a suspect, you pay attention. Atlas and Bennu share a chemical fingerprint. One preserved it, the other is manufacturing it. That's not a coincidence you can easily dismiss. So what does this mean? One possibility is that Bennu is a fragment of an ancient object that behaved like Atlas. Billions of years ago, during the formation of the solar system, there might have been multiple chemically active bodies producing organics through Fischer-Tropsch synthesis and magnetite shielding. Bennu could be a remnant, a piece broken off from a larger parent body that was destroyed or ejected. The chemistry survived because the magnetite shells protected it through billions of years of cosmic exposure. If that's true, then Atlas isn't unique. It's a repeat performance, a living example of a process that once seeded the early solar system with prebiotic molecules. But here's the paradox. If Bennu's chemistry is so rare, so fragile, so dependent on specific conditions, why does Atlas have the exact same setup? Why would two objects separated by billions of years and potentially hundreds of light years of interstellar space independently develop identical chemical pathways? Natural processes can produce similar results, but they usually show variation. Every snowflake is unique. Every comet has a different composition. Yet Bennu and Atlas look like they came from the same assembly line. Contamination was the first concern. Laboratories went into overdrive, triple verifying the Bennu sample purity. No Earth-based contamination, no cross-contamination from other meteorites. The organics are genuinely extraterrestrial, genuinely ancient, and genuinely protected by magnetite shells. The data is solid, which means the connection to Atlas isn't an artifact, it's real. Some scientists are privately uncomfortable with how closely Atlas's chemistry mirrors prebiotic Earth conditions, the amino acid ratios, the sugar types, the nucleotide precursors, is almost too perfect. If you wanted to design a chemical reactor to produce the ingredients for life, you'd end up with something that looks a lot like Atlas. High carbon dioxide for carbon feedstock, water for hydrogen and reaction medium, iron and nickel for catalysis, rotation for mixing, magnetite for shielding. It's an elegant system, maybe too elegant. The natural explanation is convergent. Chemistry. Under similar conditions, chemical reactions follow predictable pathways. Fischer-Tropsch synthesis produces a specific product distribution regardless of where it happens. Magnetite forms whenever water meets iron. Rotation homogenizes fluid flow. It's all just physics and chemistry operating under consistent laws. Atlas isn't designed. It's just a really good example of what happens when you get the right ingredients in the right environment. But the timing, the activation, the shielding, the ejection geometry, the spectral match to Bennu, the ratio precision. At some point, coincidence starts looking like coordination. And that's the paradox. We have overwhelming evidence that this chemistry is natural, universal, inevitable. But we also have an object that's behaving like it was built for a specific purpose, arriving at our solar system at a specific time, activating at a specific distance, ejecting material toward a specific target. Natural or designed, we don't have enough data to choose. What we do have is March 2026 approaching fast. Earth crosses Atlas's perihelion position then. If there's organic material in stable orbits along that path, we're about to get a direct sample. Not from a canister that travelled 2.7 billion kilometres, from a cloud that travelled light years. And unlike Bennu, we won't have to wait 2 years to analyse it. It's coming to us. Part 5. The Wake Geometry. Are we walking into a delivery stream? Let me walk you through the geometry of what's about to happen. Atlas reached perihelion on November 28, 2025, passing within 0.64 astronomical units of the Sun, roughly 96 million kilometres. At that distance, solar heating maximised outgassing. Jets extended 50,000 kilometres from the nucleus. Plumes of gas, dust and organic molecules ejected at velocities reaching several hundred metres per second. Most of that material will disperse into space, pushed by solar wind, falling into the Sun, or escaping the solar system entirely, but some of it won't. Orbital mechanics is unforgiving. When you eject material from a moving object, that material inherits the object's velocity plus whatever additional speed the ejection provides. Depending on the angle and timing, some particles enter stable orbits around the Sun, not permanent orbits. Nothing in space is permanent, but stable enough to persist for months, sometimes years. Simulations run by multiple orbital dynamics groups estimate that a fraction of Atlas's ejecta, maybe 1 to 5%, could remain in orbits that intersect Earth's path for several months after perihelion. That fraction might sound small, but when you're ejecting millions of kilograms of material, 1% is still a substantial cloud. Earth's orbital path crosses Atlas's perihelion location in late March and early April 2026. Not crosses where Atlas is now. Crosses where Atlas was. The object itself will be long gone by then, speeding back toward interstellar space. But the trail it left behind, the wake of organic rich particles, some of that will still be there. Earth doesn't have to hit anything. It just has to fly through the region where those particles are orbiting, which it will. Because that's how orbital mechanics works. The math is straightforward, the timing is confirmed, the intersection is happening. Now, let's be clear about terminology. When scientists talk about a biological deposition event, they're not talking about organisms. They're not talking about bacteria or spores or anything alive. They're talking about molecules, amino acids, sugars, nucleotides, carbon chains, organic compounds that could theoretically contribute to Earth's chemical inventory. Panspermia doesn't require living cells. It just requires the building blocks, delivered intact, able to interact with existing chemistry. Earth already has these molecules. We produce them. But an external source, especially one shielded by magnetite and potentially carrying isotopic signatures distinct from terrestrial sources, would be detectable, measurable, unmistakable. Possible outcomes range from nothing to extraordinary. Nothing means the particles burn up in the upper atmosphere, fragmenting into atoms, contributing no meaningful deposition. Increased meteor activity means visible shooting stars as dust grains enter the atmosphere, potentially more than usual for that time of year. Micrograin deposition means particles small enough to survive re-entry without burning up, settling in the stratosphere or reaching the surface, available for collection and analysis. Isotopic anomalies mean detectable chemical signatures in atmospheric samples that don't match terrestrial ratios, evidence that something from Atlas reached us. Earth has passed through comet debris before. Every meteor shower is a passage through an old comet trail. We see Perseids every August from Comet Swift-Tuttle. We see Leonids every November from Comet Tempel-Tuttle. But those are ancient, cold, inactive trails. The organics degraded long ago. The chemistry is simple. What we're about to pass through is different. Atlas is fresh, active, chemically rich. Its ejecta contains complex organics, possibly shielded by magnetite, ejected just months earlier. We've never intersected a trail like that before. We don't have historical precedent. We're making new precedent in March 2026. Panspermia, the idea that life or its precursors spread through space, has two versions. Natural panspermia says it happens randomly. Meteorites carry organics. Comets deliver water. Life's ingredients distribute themselves across the galaxy through unguided cosmic processes. Directed panspermia says someone sends them. An advanced civilization deliberately spreads biological material to potentially habitable worlds using asteroids, comets, or purpose-built objects as delivery systems. Most scientists favour natural panspermia because it requires no assumptions about extraterrestrial intelligence. It's just chemistry, physics, and probability playing out across billions of years. But Atlas tests that assumption. If panspermia is purely natural, then activation timing shouldn't matter. Chemistry happens when conditions allow. Yet Atlas activated precisely when entering a habitable zone flux range. Precisely at a distance where liquid water becomes possible. Precisely at a time that results in Earth crossing its wake. One coincidence is interesting. Two coincidences are suspicious. Three or more coincidences demand explanation. Natural processes don't optimize for specific targets. They scatter randomly. Directed processes aim. Atlas is aimed at us. Maybe not intentionally. Maybe just as a byproduct of physics and geometry, but aimed nonetheless. So what happens in March? The conservative answer is we collect some unusual dust. Atmospheric monitoring stations might detect elevated organic concentrations for a few days. Meteorite hunters might find samples with interesting isotope ratios. Scientists will analyse, debate, publish papers. Life continues. The radical answer is we get proof. Proof that interstellar objects can deliver complex organics to planets. Proof that Fischer-Tropsch chemistry works in space. Proof that magnetite shielding preserves molecules for millions of years. Proof that Earth's biology might owe a debt to the cosmos in ways we never fully appreciated. Either way, something changes in March. We cross a line. We intersect an object that's been dormant for 10 million years, woke up when it entered our solar system, produced the building blocks of life in real time, and left a trail directly in our path. That's not speculation. That's observation. The question isn't whether it's happening. The question is what it means. And we're about to find out if Atlas is a factory, if Bennu is the archive, if the chemistry is real, if the timing is more than coincidence, then what triggered it? What broke 10 million years of silence? Why now? Why us? Those are the questions that keep scientists awake at night. And those are the questions we're diving into next. Part 6. The Fischer-Tropsch hypothesis. Finally matures. Let's talk about making life from rocks. Fischer-Tropsch synthesis is a chemical process discovered in 1925 by two German chemists, Franz Fischer and Hans Tropsch. They figured out how to turn carbon monoxide and hydrogen gas into liquid hydrocarbons using metal catalysts at elevated temperatures and pressures. It's the same process Nazi Germany used during World War II to make synthetic fuel from coal. It's the same process modern industries use to produce diesel from natural gas. And it might be the same process that created the building blocks of life on Earth, and possibly throughout the universe. Here's how it works in simple terms. You start with carbon monoxide or carbon dioxide and molecular hydrogen. You need a catalyst, usually iron, nickel, cobalt or ruthenium, metals that speed up chemical reactions without being consumed. You apply heat, typically between 200 and 300 degrees Celsius, and moderate pressure. The carbon and hydrogen atoms rearrange themselves into chains. Short chains become gases, medium chains become liquids, long chains become waxes. Along the way, you also produce alcohols, aldehydes, ketones, and with the right conditions, amino acids and sugars. The exact products depend on temperature, pressure, catalyst type, and reaction time. But the core principle is universal. Combine simple gases with metal catalysts and energy, and you get complex organic molecules. Iron-nickel meteorites are perfect Fischer-Tropsch reactors. They're loaded with catalytic metals. They contain carbon from ancient stellar processes. When they collide with icy bodies, they introduce water, which breaks down into hydrogen and oxygen. The oxygen oxidizes the metal, forming magnetite and releasing hydrogen. The hydrogen combines with carbon dioxide or carbon monoxide, catalyzed by the remaining metallic iron and nickel. Heat from impacts, radioactive decay, or solar radiation drives the reaction. You don't need a laboratory. You don't need sophisticated equipment. You just need the right ingredients in the right place at the right time. And space is full of the right ingredients. Atlas has everything. Iron-rich core, nickel deposits, carbon dioxide at 8 times the concentration of water, providing abundant carbon feedstock. Liquid water circulating through the interior, dissociating into hydrogen and oxygen. Solar heating maintaining temperatures in the range where Fischer-Tropsch reactions are efficient. Rotation homogenizing the internal environment, preventing dead zones where reactants can't reach catalysts. It's a textbook setup. If you wanted to design a space-based organic synthesis reactor, you'd build something that looks exactly like Atlas. Bennu's sample composition supports this hypothesis. The amino acids found in Bennu match the expected product distribution from Fischer-Tropsch pathways, not perfectly. Natural systems are never perfect, but the ratios, the chirality, the molecular weights, they align with what you'd predict from catalytic synthesis, rather than random organic accumulation. The sugars, ribose and glucose, are Fischer-Tropsch compatible. The nucleotides, harder to produce but still possible under extended reaction times with the right precursors. Bennu looks like the output of a Fischer-Tropsch reactor that ran for millions of years, then froze, preserving the products in magnetite shells. Now, here's where Atlas takes it further. We're not looking at frozen remnants, we're watching active synthesis. Spectroscopy detects organics in states consistent with fresh production. The carbon-to-hydrogen ratios shift over time, indicating ongoing reactions. The temperature profiles show localized hotspots where catalytic activity is concentrated. Atlas isn't just a rock with organics inside. It's a functioning chemical plant, processing raw materials into complex molecules as it travels through space. And because it's doing this now, while we're watching, we can study the process in real time. We can measure reaction rates. We can track product evolution. We can test whether Fischer-Tropsch synthesis really can produce prebiotic molecules under space conditions. We don't have to rely on models or simulations. We have the real thing. The maturation of the Fischer-Tropsch hypothesis is this. It's no longer speculative. We have laboratory evidence that the reactions work. We have meteorite samples showing the products exist. We have an active interstellar object demonstrating the process in progress. The pieces fit together. The chemistry is consistent. The physics is sound. Life's building blocks don't require exotic conditions or rare events. They require carbon, hydrogen, metals, water, and energy, all of which are abundant in the universe. Fischer-Tropsch synthesis might be the default pathway for organic molecule formation anywhere those ingredients coexist. Not special, not rare, universal. If that's true, then Atlas isn't an anomaly. It's an example. One of countless objects throughout the galaxy doing the same thing, converting simple gases into complex organics, distributing those organics through space, delivering them to planets, moons, asteroids, anywhere the wake intersects. Earth might have received dozens, hundreds, thousands of these deliveries over its 4.5 billion year history. Some impacted directly, some deposited molecules in the upper atmosphere, some passed through without interacting. But each one contributed a little bit to the chemical inventory that eventually led to life. We're not just watching Atlas. We're watching the process that might have seeded Earth. But if Fischer-Tropsch synthesis is universal, if it happens anywhere the ingredients exist, then why did Atlas wait 10 million years to start? Why didn't it activate while travelling through interstellar space? What's special about our solar system that triggered the reaction? That's the question that keeps coming back. The chemistry makes sense. The physics makes sense, the evidence makes sense, but the timing doesn't. Unless there's something about crossing the heliosphere, entering the sun's domain that flips a switch. Unless Atlas wasn't just waiting for heat, it was waiting for something else. Part 7. The 10 million year silence and the trigger problem. Atlas travelled through interstellar space for at least 10 million years. We know this from its velocity and trajectory, tracing back to its likely origin in the direction of the constellation Ursa Major. 10 million years is a long time. Long enough to pass multiple star systems. Long enough to experience varying radiation environments, gravitational perturbations, occasional close approaches to other objects. Yet Atlas remained dormant the entire time. No brightening events recorded. No activity detected by telescopes monitoring interstellar space. It was just a dark rock moving through the void at 28 kilometers per second. Until it entered our solar system. Then it woke up. The question is why? What changed? The obvious answer is sunlight. Stars produce heat and radiation. As Atlas approached the sun, solar flux increased, heating the surface and interior, melting subsurface ice, triggering the phase transition we observed at 2.5 AU. Simple, straightforward. Except Atlas passed other stars during its 10 million year journey. None of them activated it. Our Sun is a G-type main sequence star. Spectral class G2, nothing unusual. There are billions of similar stars in the galaxy. If solar heating alone was sufficient, Atlas should have activated multiple times during its travels. It didn't. So what's different about our Sun? Or more precisely, what's different about our solar system? One possibility is the heliosphere. The heliosphere is the bubble of charged particles and magnetic fields generated by the Sun, extending roughly 100 AU outward, where solar wind pressure balances interstellar medium pressure. Crossing the heliopause, the boundary of the heliosphere, exposes an object to a sudden shift in plasma density, magnetic field orientation, and charged particle flux. Voyager 1 crossed the heliopause in 2012 and detected dramatic changes in cosmic ray intensity and plasma composition. Could that transition trigger chemical processes inside Atlas? Maybe, but we don't have enough data to confirm. Another possibility is tidal forces. As Atlas approached the Sun, tidal stress increased, potentially cracking the interior, creating new pathways for water circulation, exposing fresh catalytic surfaces. Tidal activation happens with moons. Jupiter's moon Io is volcanically active because tidal flexing generates internal heat. Saturn's moon Enceladus ejects water plumes for the same reason. But Atlas is much farther from the Sun than these moons are from their planets. Tidal forces at 2.5 AU are weak, probably not enough to crack a solid body unless it was already structurally compromised. Possible, but not definitive. The third possibility is cumulative energy storage. Over 10 million years, even tiny amounts of radioactive decay, residual heat from formation, or energy absorbed from cosmic rays could accumulate inside a well-insulated object. If the interior is mostly ice with pockets of liquid brine maintained by dissolved salts or ammonia, heat doesn't escape quickly. It builds. When external heating from the Sun pushes the system past a critical threshold, the stored energy releases suddenly, triggering the phase transition. Think of it like a battery slowly charging over millions of years, then discharging rapidly when connected to a circuit. The Sun didn't create all the energy. It just provided the final push to release what was already there. These are all natural explanations, defensible, supported by physics, but none of them fully explain the timing precision. Atlas didn't activate gradually. It didn't show pre-brightening signs. It went from dormant to active in less than 72 hours. That's not a slow threshold crossing. That's a switch. And switches imply either very specific conditions or very specific responses to those conditions. Natural systems can have switch-like behavior. Phase transitions often exhibit sudden changes. Water doesn't gradually turn to steam. It boils abruptly when temperature crosses 100 degrees Celsius at standard pressure. Maybe Atlas experienced something similar. A thermal threshold, a chemical threshold, a structural threshold that once crossed initiated rapid change. But here's the uncomfortable question. If the threshold is natural, why is it tuned to habitable zone flux levels? 2.5 AU is roughly where Mars orbits. It's the inner edge of the habitable zone for some stellar models. It's where solar radiation is strong enough to maintain liquid water with minimal atmospheric pressure. If you wanted to design an activation system that only triggers near potentially habitable planets, you'd set the threshold exactly where Atlas activated. Not closer, because too much heat would destroy the organics. Not farther, because reactions would be too slow, right at the edge, right where Earth-like conditions begin. That's either the most extraordinary coincidence in cosmic history, or it's engineered. Not with computer chips and wires, with chemistry, with material selection, with structural design that responds to specific energy inputs. If an advanced civilization wanted to distribute prebiotic molecules to habitable worlds without active guidance systems, they'd build objects that activate automatically when exposed to habitable zone radiation, self-triggering, self-regulating, self-distributing. You wouldn't need to aim them at specific planets. You'd just send millions of them into the galaxy, let them drift, and trust that the ones entering systems with habitable zones would activate naturally. The chemistry does the work. The physics does the targeting. No intelligence required at the destination, just at the origin. Is that what Atlas is? A 10-million-year-old message in a bottle designed to open only when it reaches the right environment? We don't have enough evidence to claim that definitively. What we have is an object that behaves exactly how such a system would behave. Dormant in interstellar space, activated in a habitable zone, producing life's building blocks, ejecting them toward planetary orbits, timed to intersect Earth's path months after activation. If you saw those characteristics in an artificial system, you'd call it a probe. But Atlas is made of rock and ice. It has no electronics, no engines, no obvious technology. So we call it a comet and try to explain away the coincidences. Maybe we're right. Maybe natural processes can fine-tune activation thresholds to habitable zone flux levels through sheer accident. Or maybe we're missing something. Maybe the line between natural and designed is thinner than we thought. Maybe chemistry can encode intent without consciousness. Maybe the universe is stranger than we're comfortable admitting. And maybe in March 2026, when Earth passes through Atlas's wake, we'll get our first hint of an answer. Part 8. Directed panspermia versus emergent panspermia. Panspermia is the idea that life or its precursors travel through space, spreading from one world to another. It's not a new concept. The Greek philosopher Anaxagoras proposed it in the 5th century BCE. Modern scientists revived it in the 20th century as we discovered organic molecules in meteorites and realized that microbes could survive space conditions. But panspermia splits into two camps, and they're fighting over Atlas. Emergent panspermia says life's building blocks spread naturally. No intent, no design, just cosmic billiards. Comets and asteroids collide. Material ejects into space. Some of it lands on planets. Repeat for billions of years, and eventually prebiotic molecules accumulate on worlds with the right conditions. Life emerges wherever the chemistry allows. Earth might be one success story among millions, or billions. The universe is big. Probability works in life's favour given enough time and space. Emergent panspermia requires no intelligence, no coordination, no purpose. It's chemistry and physics doing what they do. Random, messy, eventual. Directed panspermia says someone sent it. An advanced civilization deliberately distributes biological material to potentially habitable worlds, maybe to seed new biospheres, maybe to preserve their own legacy, maybe as an experiment. The method could vary. Spacecraft carrying microbial payloads, engineered asteroids loaded with organics, comets modified to activate in habitable zones. The key distinction is intent. Directed panspermia requires a sender, a decision, a goal. It's not random, it's purposeful. And if it's happening, we should see evidence. Patterns, optimization, design choices that natural processes wouldn't make. Atlas fuels both camps, and that's what makes it so contentious. The natural camp points to the chemistry. Fischer-Tropsch synthesis is well understood. Magnetite formation is basic geology. Comets outgoes all the time. Atlas is just a particularly rich example. Yes, the timing is unusual. Yes, the activation is clean. Yes, the composition matches Bennu's. But unusual doesn't mean artificial. It means rare. Space is vast. Rare events happen. Atlas is a rare comet with a Rare composition that happened to enter our solar system at a time when we had the technology to observe it in detail. Lucky timing, nothing more. The directed camp points to the anomalies. The 4.5 sigma carbon dioxide to water ratio. Statistical significance matters. 4.5 sigma means there's a 1 in 300,000 chance that ratio occurred randomly. That's not just unusual, that's engineered. The activation at exactly 2.5 AU, the sunward jet, the magnetite shielding, the spectral match to prebiotic Earth chemistry, the ejection timing that intersects Earth's orbit. Any one of those could be coincidence. All of them together, that's a pattern, and patterns imply organization. Natural processes produce noise, design produces signal, Atlas is signaling. The question is whether anyone sent it or whether the universe itself is the sender. There's a middle ground that both camps are uncomfortable acknowledging. Maybe the line between emergent and directed is artificial. Maybe chemistry can encode logic without consciousness. DNA stores information. RNA catalyzes reactions. Prions propagate structure, all without thought or intent. They just follow rules. If you set up the right chemical system, it can exhibit behavior that looks purposeful. Activation thresholds, self-assembly, replication, all emergent from molecular interactions. No designer needed, just the right conditions. What if Atlas is that kind of system? What if the chemistry is optimized not because someone built it, but because that's the stable configuration that survives? Objects with poorly tuned activation thresholds either activate too early and disperse their organics uselessly, or they never activate and remain sterile. Only objects with habitable zone activation survive long enough to deliver molecules to planets. It's not design, it's selection. Cosmic natural selection operating on chemical systems over billions of years. The ones that work persist, the ones that don't vanish. Atlas might be a survivor, a configuration that's been refined through countless iterations across the galaxy, not by intelligence, but by chemistry, favouring stable, effective pathways. That possibility terrifies both camps, because it means neither is entirely right. It means life's spread isn't random, but it's not directed either. It's inevitable. A cosmic algorithm running in the background of every solar system, optimizing delivery systems, refining activation parameters, distributing molecules wherever conditions allow. Intelligence doesn't create it. Intelligence emerges from it. We're not the designers. We're the product. And Atlas? Atlas is just one line of code in a program that's been running for billions of years, self-modifying, self-optimizing, self-distributing across the galaxy. No consciousness, no purpose, just chemistry doing what chemistry does best, evolving towards stability. Or maybe that's too comforting. Maybe the directed camp is right. Maybe someone, somewhere, 10 million years ago, sent Atlas toward our solar system with specific instructions encoded in its chemistry. Wake when you enter a habitable zone. Produce organics. Eject toward planetary orbits. Deliver. The sender is long gone. The message remains. We're about to receive it. And we don't know if it's a gift or a warning or just information. But in March 2026, we find out. Because whether Atlas is natural, designed, or something in between, the result is the same. Earth intersects its wake. Molecules enter our atmosphere. Chemistry interacts. Something changes, maybe imperceptibly, maybe profoundly, but something. Part 9. The Magnetic Cocoon Conjecture. Comets shouldn't have magnetic fields. They're ice and rock, non-conductive materials that don't generate magnetism. Earth's magnetic field comes from a molten iron core churning like a dynamo. Comet nuclei are solid, frozen, inert. No motion, no currents, no fields. Except that's not entirely true. Comet 67P taught us that comets can develop temporary magnetospheres through plasma interactions with the solar wind. The Rosetta spacecraft measured magnetic field strengths up to 300 nanoteslas near the nucleus, weak but detectable, caused by charged particles from outgassing interacting with the sun's magnetic field. It's not a dynamo, it's induced magnetism, borrowed from the environment. Atlas might be doing something different, something stronger, something that persists rather than fluctuates. The key is magnetite, iron oxide, magnetic mineral. When water reacts with metallic iron and nickel inside Atlas, magnetite forms as a byproduct. If the interior is continuously producing magnetite through ongoing Fischer-Tropsch reactions, and if that magnetite accumulates in specific zones rather than dispersing evenly, You could build up a significant magnetic signature over time. Not a dynamo field, a frozen-in field, locked into the solid structure of the nucleus, permanent rather than induced. Rotation helps. Atlas spins every 16.6 hours. If liquid water is circulating through the interior, carrying dissolved ions, that's a moving electrical conductor. Moving charges create magnetic fields. It's basic electromagnetism. The effect would be weak compared to Earth's dynamo, but it wouldn't be zero. Combine a weak dynamo effect from liquid circulation with permanent magnetization from accumulated magnetite, and you get a hybrid system. Part induced, part frozen, part active. A magnetic cocoon. Why does this matter? Radiation shielding. Cosmic rays are high-energy particles, mostly protons, travelling through space at nearly light speed. When they hit organic molecules, they break chemical bonds, fragment structures, sterilize. Magnetite blocks radiation physically, but a magnetic field deflects it. Charged particles follow magnetic field lines. If Atlas has a magnetosphere, even a weak one, it creates a bubble where radiation intensity drops, not eliminated, reduced. Enough to significantly extend the survival time of complex organics. Bennu's samples showed this. Magnetite shells preserved molecules for billions of years. A magnetosphere adds another layer of protection, a larger-scale shield that doesn't just protect individual molecules, but the entire interior environment. The sunward jet supports this hypothesis. If Atlas has a magnetosphere, plasma interactions shape outgassing into directed streams. The solar wind carries its own magnetic field. When it encounters Atlas's field, they interact, creating pressure points, flow channels, deflection zones. Material ejected from the nucleus doesn't just expand spherically, it follows magnetic field lines, creating jets that can point in directions that seem physically contradictory. The sunward jet isn't fighting the solar wind, it's riding a magnetic pathway created by field line reconnection. Same physics that causes solar flares and auroras on Earth. Scaled down, but fundamentally identical. Rotation matters again here. If the magnetic field is rotating with the nucleus, it sweeps through space like a lighthouse beam. Material ejected at specific points in the rotation gets caught in different field configurations, producing multiple jets at different angles. The sunward jet might be the dominant feature we're seeing now, but there could be others, weaker or pointing in directions harder to observe. The overall effect is a structured outgassing pattern, rather than random venting. Structure implies order. Order implies either design or stable configuration. Atlas is either very carefully built or very efficiently self-organized. The magnetic cocoon hypothesis doesn't tell us which. It just tells us the mechanism. Here's the speculative part. If Atlas's magnetosphere is protecting its interior from radiation, and if that protection has been active for millions of years, then the organics being produced and stored inside are pristine. No degradation from cosmic rays, no fragmentation from ultraviolet light, just pure complex molecules, synthesized through Fischer-Tropsch pathways, coated in magnetite, suspended in liquid water or ice depending on depth and temperature. When Atlas ejects this material at perihelion, it's not releasing ancient degraded residues. It's releasing fresh, intact, biologically relevant molecules, shielded all the way from production to ejection. And if those molecules enter Earth's atmosphere in March 2026, they arrive in better condition than any meteorite organics we've ever analysed. That's the delivery capsule concept. Atlas isn't just a factory. It's a shipping container designed or evolved to preserve its cargo across interstellar distances, through millions of years of travel until it reaches a destination. The activation timing ensures the factory runs only when needed. The magnetic cocoon ensures the products survive. The ejection geometry ensures they reach planetary orbits. It's a complete system, and whether that system arose naturally or was constructed, it works. We're about to see how well. But there's a darker possibility that the magnetic cocoon raises. If Atlas can shield its interior from radiation for millions of years, what else could survive inside? Organic molecules, yes. But what about more complex structures? Prions, viruses, dormant spores? We have no evidence that Atlas carries anything like that. The spectroscopy shows simple organics, amino acids, sugars, no biosignatures of actual life. But magnetic shielding changes the survival calculus. Things that should have been destroyed by radiation might persist. Things we assume couldn't travel through space might have found a way. And if Atlas isn't unique, if there are others like it, dormant or active, scattered through the galaxy, then the question isn't just what Atlas delivers to Earth. It's what's already been delivered. How many times has Earth passed through similar wakes without noticing? How much of our chemistry, our biology, our evolutionary history was influenced by invisible depositions from objects we never saw? Atlas is the first one we're watching. But it might not be the first one we've encountered. Part 10. The Hidden Players, Agencies, Groups and Quiet Meetings. Something shifted after the Bennu sugar announcement. Publicly, NASA released the data, scientists published papers, press conferences happened, the media covered it. Standard procedure. But behind the scenes, telescopes started retasking. Observatories that hadn't scheduled Atlas observations suddenly requested time. Ground-based instruments in Chile, Hawaii, the Canary Islands, all pivoting toward one object. That doesn't happen casually. Telescope time is precious, allocated months or years in advance. When multiple facilities simultaneously rearrange priorities, someone made calls. Someone decided Atlas was worth disrupting everything else. The classified data issue surfaced briefly in November. NASA and ESA temporarily restricted access to certain Atlas spectral datasets, citing data quality verification. Standard excuse usually means they found something unexpected and want to understand it before releasing it publicly to avoid misinterpretation or error. The restriction lasted 4 days. When they lifted it, the data showed the carbon dioxide to water ratio, the organic signatures, the anomalies we've been discussing. But 4 days is a long time when observatories worldwide are watching. What were they verifying, or deciding how to present? JAXA, the Japan Aerospace Exploration Agency, made an unusual demand in early December. They requested raw spectral feeds from the Subaru telescope and the Atacama Large Millimeter Array. Not processed data, raw. That suggests they wanted to run their own analysis independent of Western institutions, either because they doubted the conclusions or because they had their own models and needed unfiltered inputs. JAXA's involvement isn't surprising. They've been leaders in asteroid and comet science since Hayabusa. But the urgency was notable. Requests were marked high priority. Resources were redirected. Someone in Japan is very concerned about Atlas. Private scientific institutes started holding off-the-record discussions in late November. Not public conferences, closed meetings, attendees under non-disclosure agreements. Topics officially listed as astrobiology risk assessment or interstellar object impact modelling. Risk assessment is code for what happens if this goes wrong. Impact modelling is code for are we in danger? These aren't academic curiosities. These are operational planning sessions. Someone is preparing for contingencies. Why the secrecy? 2 fears. Fear number 1 is public panic over alien contamination. The word alien triggers irrationality. Scientists know that. They remember the Martian meteorite hysteria in 1996 when NASA announced possible fossil bacteria in ALH 84001. Media went wild. Public divided between excitement and terror. Later analysis cast doubt on the biosignatures, but the damage was done. Trust eroded. Atlas is worse. It's not a meteorite. It's an active object producing organics in real time, heading toward Earth's orbital path. If media frames it as alien biological attack, rational discussion evaporates. Agencies want to avoid that, so they control the narrative, release information slowly, emphasize natural explanations, downplay directed panspermia speculation. Fear number 2 is scientific embarrassment. What if the March 2026 wake passage produces nothing? What if all the build-up, the theories, the preparations result in a non-event? Earth flies through the wake. Nothing happens. No detectable deposition, no isotopic anomalies, no increased meteor activity. Just silence. Scientists who pushed for telescope time, diverted resources, held classified meetings, they'll look like they overreacted. Funding agencies will question judgment. Public will mock. Academia is brutal about failed predictions. Better to stay quiet, observe, analyze, then announce findings only after confirmation. Under-promise, over-deliver. Quiet collaboration is happening behind the scenes. Multiple agencies building cross-model predictions. NASA's Jet Propulsion Laboratory running trajectory simulations. ESA's Space Situational Awareness Program tracking particles, Russian Academy of Sciences contributing atmospheric deposition models, China's National Space Administration providing alternative chemical analyses, not publicized, not coordinated through official channels, just scientists emailing scientists sharing data, comparing results. When official collaboration is too slow or too politicized, informal networks take over. Atlas data is flowing through those networks now. The consensus emerging is cautious concern, not panic, not dismissal, concern, the kind that makes you check your models 3 times and keep a satellite ready just in case. The containment versus transparency debate is real and ongoing. One camp says tell people everything, let them decide how to interpret it, trust public intelligence. Another camp says manage the release, frame it carefully, prevent misinterpretation before it starts. Both sides have valid points. Both sides cite historical precedents supporting their position. No resolution yet, so they compromise, release some data publicly, keep some restricted, publish papers with careful language, avoid sensational terminology, emphasize unknowns, acknowledge possibilities without endorsing conclusions. It's bureaucratic language designed to say everything and nothing simultaneously. Frustrating for outsiders, necessary for insiders. Governments are involved, but quietly. National security agencies monitor anything entering Earth's atmosphere. Atlas isn't a threat in the kinetic sense. It's not going to hit us. But biological risk is still risk. If the wake contains something unexpected, something that interacts with Earth's biosphere in unforeseen ways, response plans need to exist. Not public plans, classified plans, the kind drawn up for pandemic outbreaks or chemical weapons releases. Extreme low probability, but extreme high consequence. So contingency planners run scenarios, model worst cases, identify choke points, prep responses, then file the plans and hope they're never needed. This is all happening while you're reading headlines about sports and politics and celebrity gossip. Atlas is a background hum in the scientific community, growing louder as March approaches, but still background. Most people don't know it exists. Those who do mostly think it's just another comet. Only a few thousand people worldwide are deeply engaged with the data, running the models, watching the approach. And among them, even fewer are asking the uncomfortable questions. What if we're wrong about it being natural? What if March brings more than molecules? What if the 10 million year journey wasn't random? Asking those questions publicly gets you labelled a crank. Asking them privately gets you invited to the meetings, the ones that don't appear on any schedule, where the real discussions happen, where the real concerns are voiced, and where, quietly, people are preparing for March 2026 not as a scientific curiosity, but as a potential threshold event. Not end of the world, not first contact, just a moment where Earth's story might pivot slightly, or might not. But you don't ignore that possibility. You prepare, and you stay quiet, because if you're wrong, you look foolish. But if you're right and unprepared, that's unforgivable. Part 11. December 2025. The synthetic protein that self-assembles without DNA. While everyone was watching Atlas, a laboratory, in Cambridge dropped a paper that might have just solved one of biology's oldest mysteries. December 14th, 2025. The headline was dry, academic, the kind that gets buried on page 6. But what it described was extraordinary. Researchers created peptide chains, short protein-like molecules that self-assembled on mineral surfaces using only electric fields. No DNA, no RNA, no enzymes, just amino acids, clay minerals, salt water, and voltage. The peptides formed, folded, and exhibited catalytic activity, meaning they could speed up chemical reactions like real proteins, lifelike structures without any biological machinery. Let me explain why that matters. The central dogma of biology is DNA makes RNA makes protein. Proteins do the work. DNA stores the instructions. RNA translates. That's how life operates now. But that's not how it started. DNA is too complex to emerge first. Something simpler had to precede it. Scientists have suspected for decades that the first life used RNA or protein-like molecules that could both store information and catalyze reactions. But making proteins without existing biology is incredibly difficult, Amino acids don't just spontaneously link up into chains, they need energy, activation, catalysts. The chicken and egg problem. Proteins need biology, but biology needs proteins. The Cambridge team solved it with minerals, specifically montmorillonite clay. Clay has layered structure with charged surfaces. When amino acids dissolve in water near clay, they adsorb onto the surface, lining up in patterns determined by the mineral's crystal structure. Apply an electric field, which could come from geothermal gradients, lightning or electrochemical cells in hydrothermal vents, and the amino acids link together. The electric field provides energy. The clay provides structure. The amino acids provide material. Result is peptide chains up to 50 amino acids long, capable of folding into shapes that mimic proteins. Laboratory reproduction was simple, embarrassingly simple. Undergraduate level equipment, clay powder, amino acid solution, electrodes, run current for a few hours, extract peptides, analyze, repeat. Success rate was high. Over 80% of trials produced peptides. Some even showed chirality preference, meaning left-handed amino acids linked more readily than right-handed, matching the bias seen in terrestrial life. Nobody programmed that. It emerged from the physics of molecular interactions on mineral surfaces. The universe has a preference. Chemistry leans left, not by design, by energy minimization. Left-handed configurations are slightly more stable under certain electric field conditions. Scale that up over millions of reactions, and you get a planet where proteins are left-handed. Everywhere, including us. Implications ripple outward. If proteins can form on mineral surfaces without biology, then prebiotic chemistry is far easier than we assumed. You don't need rare conditions. You don't need lightning-striking primordial soup at exactly the right moment. You just need wet minerals and energy gradients, which exist on every planet with liquid water and geological activity. Mars had it. Europa has it now. Enceladus has it. Titan probably has it. Every world with subsurface oceans and hydrothermal vents is running the same experiment Earth ran 4 billion years ago. Some succeed, some fail, but the starting conditions are universal. This connects directly to Atlas. The interior is loaded with minerals, metallic iron, nickel, silicates, magnetite forming in real time, liquid water circulating, heat gradients from solar warming and possibly internal reactions, electric currents from charged particle interactions and possibly weak dynamo effects. Everything the Cambridge experiment requires, Atlas has, naturally, at scale, for millions of years. If peptides self-assemble on mineral surfaces in laboratories, they self-assemble inside Atlas. And if Atlas is ejecting those peptides into space, coated in magnetite for radiation protection, then the weight contains not just amino acids but peptide chains, protoproteins, molecules one step closer to biology than raw building blocks. The philosophical question is whether life is inevitable or rare. Rare means Earth got lucky. Inevitable means Earth was always going to happen, here or elsewhere, because chemistry follows predictable pathways under common conditions. The Cambridge experiment leans toward inevitable. If peptides form spontaneously, wherever amino acids meet minerals and energy, then life's emergence is less about chance and more about time. Give chemistry enough opportunities, and it finds the pathway. Life isn't a miracle. It's a stable configuration that chemistry keeps discovering because it's thermodynamically favourable. That undermines the argument that Bennu's chemistry is improbable. If organics form easily, if peptides assemble spontaneously, if minerals catalyse the process, then finding complex molecules on asteroids isn't surprising. It's expected. Bennu isn't special, it's typical. Every carbonaceous asteroid probably has similar chemistry, just hidden deeper or less accessible. We've only scratched the surface, literally, of one object. Sample return missions to other asteroids will likely find the same patterns: sugars, amino acids, nucleotides, peptides, all preserved in magnetite shells, all waiting to be discovered, all evidence that the universe is saturated with prebiotic chemistry everywhere the conditions allow, which makes Atlas even more interesting. If peptide formation is universal, and Atlas is actively producing amino acids, then it's probably producing peptides too. We haven't detected them yet. Spectroscopy has limits. Peptides are harder to identify remotely than simple molecules. But if the Cambridge results apply, and there's no reason they shouldn't, then Atlas's interior is a peptide factory, self-assembling chains forming on magnetite, and silicate surfaces folding into shapes, potentially even exhibiting catalytic activity, all inside a 10-kilometre ball of ice and rock hurtling through space. Not alive, not even close, but closer than anything we've created in a lab without using biology as a starting point. Hydrothermal vent theories gain support from this too. The theory that life started at undersea vents where hot mineral-rich water meets cold seawater, creating chemical gradients and energy flows. Cambridge's work shows that's plausible. Minerals plus water plus energy equals peptides. Vents provide all three. Early Earth had vents. Modern Earth still has vents. Some support ecosystems independent of sunlight, fueled entirely by chemical energy. Life at vents doesn't need photosynthesis. It needs chemistry. If that's how terrestrial life started, then anywhere with vents could start life too. Not just Earth, not just now, anywhere, any time, given enough opportunity. Atlas might represent an interstellar vent, not biological, but chemically equivalent, producing the same molecules, following the same pathways, demonstrating the same principles. If we can study Atlas's chemistry in detail, map its internal structure, model its reaction zones, we might be looking at a preserved snapshot of what early Earth looked like before biology emerged. A prebiotic factory still running, still making the building blocks, waiting for the next step that turns chemistry into life. Earth took that step. Atlas hasn't. Maybe it can't. Maybe it's missing something, some critical catalyst or environmental condition, or maybe it's just waiting. Waiting for its cargo to reach a world where the next step is possible. Waiting for March. Waiting for us. Part 12. The new AI-modelled prebiotic Earth map dropped this month. On December 20th, 2025, a team at MIT released something that's been quietly brewing in AI labs for the past 2 years. They trained a large language model, not on text, but on chemistry, fed it every known reaction pathway, every thermodynamic dataset, every geological record of early Earth conditions they could find. Then they asked it a question. What was Earth's chemical inventory 4 billion years ago? And the AI built a map. Not a geographic map, a chemical map. Concentrations of carbon dioxide, methane, ammonia, hydrogen sulfide, water vapour, across different regions, different altitudes, different ocean depths. Temperature gradients, pH levels, mineral compositions, energy fluxes from volcanic activity, lightning, ultraviolet radiation, meteor impacts. The model didn't just estimate, it simulated. Billions of virtual reactions per second, evolving the chemistry forward in time, predicting which molecules would form, where they'd accumulate, how they'd interact. The output was a dynamic three-dimensional picture of prebiotic Earth's chemical landscape. And it was shocking. The AI predicted that certain zones, specifically shallow hydrothermal pools in volcanic regions, would have organic precursor concentrations orders of magnitude higher than other environments. The ratios of amino acids, sugars, nucleotides matched Bennu's sample composition in multiple categories. Not perfectly. Close enough that when the results were first presented, some scientists accused the team of overfitting the model to known data. They hadn't. The model was trained on terrestrial geology and basic chemistry. It had never seen Bennu's results. Yet it predicted similar ratios independently. That's either an extraordinary validation of the model's accuracy or evidence that Bennu-like chemistry is a natural outcome of common prebiotic conditions. Either way, it's significant. The AI also predicted ribose formation zones. Ribose, the sugar that's notoriously fragile, the holy grail molecule we found on Bennu. The model identified specific environmental niches where ribose could form and persist for extended periods. High pH, moderate temperature, presence of borate minerals which stabilize ribose against degradation. Early Earth had those zones, not everywhere, but enough that ribose wasn't a freak occurrence. It was an expected product in the right locations, which means life didn't have to get lucky to access ribose. Life just had to emerge in the zones where ribose was already available. This introduces the concept of universal chemistry pathways. Chemistry isn't random. It follows rules. Thermodynamics, kinetics, reaction equilibria. Under similar conditions, similar reactions occur. If early Earth and Atlas share similar conditions, high carbon dioxide, liquid water, metal catalysts, energy gradients, then they'll produce similar molecules. It's not coincidence, it's physics. The AI model supports this. When you simulate prebiotic environments, you get a narrow range of likely products. Amino acids, sugars, nucleotides, lipids. The building blocks of life aren't special. They're inevitable outputs of common chemistry. Relevance for Atlas is immediate. If the AI model accurately recreates early Earth chemistry, and if that chemistry matches Bennu's samples, and if Atlas is currently producing the same molecules, then Atlas isn't following some alien blueprint. It's following nature's blueprint, the same one Earth followed, the same one probably every planet with the right conditions follows. Life's emergence isn't about finding the secret recipe. It's about mixing common ingredients under common conditions and letting thermodynamics do the rest. Atlas is doing that now. Earth did it 4 billion years ago. The process is universal, the timing is local, but the outcome, given enough time and stable conditions, is predictable. The AI model also forecasts chemical evolution. Once you have amino acids and sugars, what forms next? Peptides, as we discussed. Then more complex polymers. Then primitive membranes from lipids. Then encapsulated reaction systems where chemistry becomes self-sustaining. The model doesn't simulate life. It simulates the steps before life. And those steps look deterministic. Not guaranteed, but highly probable if conditions persist. Earth's chemistry walked that path. The AI model retroactively traced the footsteps. Now we can look at other environments, other worlds, other objects, and ask, are they on the same path? Atlas might be. Enceladus might be. Europa might be. Not alive, but walking toward it. The stakes for March 2026 just got higher. If AI models can predict chemical inventories from environmental conditions, then we can model what Atlas's wake contains before Earth intersects it. We don't have to wait for samples. We can forecast, feed the AI Atlas's spectroscopy data, its temperature profiles, its composition estimates. Let it simulate what molecules are likely present, what ratios, what states. Then compare that forecast to actual atmospheric measurements during the wake passage. If they match, the model works. If they don't, we learn something new. Either way, March becomes a test, not just of Atlas, of our understanding of cosmic chemistry. But there's a deeper implication. If cosmic chemistry is predictable, if AI can model it accurately, then we can forecast the probability of life elsewhere, not by searching for biosignatures directly, by mapping chemical landscapes and identifying zones where life-supporting chemistry is likely. The AI doesn't care about biology. It cares about thermodynamics, and thermodynamics is universal. Apply the same modelling approach to exoplanet atmospheres. Map their chemistry. Identify the ones following Earth-like pathways. Prioritise those for deeper observation. We might not need to find life directly. We might just need to find the chemistry that precedes it, and wait. Because if the pathways are universal, life isn't rare, it's inevitable, and Atlas might not be an anomaly. It might be the first of countless objects demonstrating the same principle. Chemistry doesn't care about borders or origins, it just cares about conditions, and the conditions for life's building blocks are everywhere. Part 13, the first nanorobotic mineral catalysis experiment, 2025 to 2026. In October 2025, a research team at Caltech did something nobody had tried before. They built micron-scale robotic particles, tiny machines smaller than a human hair, and deployed them inside porous basalt rock samples filled with water and organic precursors. The robot's job was simple: guide chemical reactions, position amino acids near catalytic iron sites, hold molecules in orientation for bonding, release products once formed, then repeat. It's chemistry, but directed. Not by intelligence, by programmed response to local chemical conditions. And it worked. The robots weren't sophisticated. No computation, no AI. Just simple mechanisms responding to pH changes and concentration gradients. When amino acid concentration increased, the robots moved toward it, attracted by chemical signals. When they encountered a catalytic surface, they oriented the amino acids for optimal bonding. The catalytic site did the rest. Peptide bond formed. Robot released the peptide, returned for another amino acid, cycled continuously. Over 72 hours, peptide concentrations in the robot-assisted samples were 40 times higher than control samples without robots. Same rock, same water, same amino acids, only difference was the robots guiding the process. Think about what 40 times means. Not 40% improvement, 4,000%. The robots didn't change the chemistry. They didn't create new reactions. They just positioned molecules more efficiently, bringing reactants to catalysts faster than random diffusion could manage. It's like the difference between hoping two people eventually bump into each other at a crowded party versus actually introducing them. The reaction was always possible. The robots just made it probable. They turned maybe into definitely, and slow into fast. The experimental setup was elegant in its simplicity. Basalt rock, the same volcanic material that covers oceanic crust and dominates Mars' surface. Ground into porous powder with millions of microscopic channels and cavities. Mixed with salt water containing dissolved amino acids at concentrations similar to what you might find in a prebiotic ocean. Iron deposits scattered throughout, providing catalytic sites. Then the robots, each one a few micrometers across, released into the mixture. No external control, no programming updates, just autonomous chemical response. The robots sensed their environment through surface chemistry. High pH on one side meant something acidic nearby. Concentration gradients meant molecules worth pursuing. Temperature variations meant energy flow, all passive sensing, all mechanical response. This demonstrates that catalytic pathways can be engineered to mimic natural systems. The robots aren't alive, they're mechanisms, but they increase reaction efficiency by orders of magnitude. Natural systems might evolve similar mechanisms without robots. Mineral surfaces with specific charge distributions that preferentially bind certain molecules, convection currents that circulate reactants past catalysts, crystal growth patterns that create channels where reactions concentrate. Nature engineers itself through physical and chemical selection. The configurations that produce results persist. The ones that don't erode. Over billions of years you get systems that look designed because inefficiency gets filtered out. Consider how rivers carve canyons. Water doesn't plan the path. It just follows gravity and resistance. Where rock is soft, erosion accelerates. Where rock is hard, water diverts. Over millennia, the most efficient drainage patterns emerge. Tributaries merge at optimal angles. Meanders form perfect, mathematical curves. Nobody designed it. Physics shaped it. The same principle applies to chemical systems. Reactions that produce stable products dominate. Reactions that consume more energy than they release fade. Catalytic surfaces that position molecules correctly get used repeatedly. Surfaces that don't remain inactive. The system self-optimizes through repeated trials across geologic time. Connect this to Atlas. Its metal-ice-carbon system resembles a vast catalytic chamber. Metallic core providing catalysts. Ice providing reactants. Rotation providing circulation, heat providing energy. If Caltech's nanorobotic experiment scales up, and there's no reason it shouldn't, then Atlas's interior is essentially a trillion times larger version of the same process. Not robots, but functional equivalents. Mineral structures guiding molecules, fluid flows positioning reactants, magnetite surfaces holding intermediates, temperature gradients driving reactions forward. It's engineered chemistry without an engineer. Just physics finding stable configurations. The scale difference is staggering. Caltech's experiment used milligrams of material in a test tube. Atlas is 10 kilometers across with a mass of trillions of kilograms. The number of potential reaction sites inside Atlas exceeds the number of atoms in all of Caltech samples by factors of billions. If even a tiny fraction of those sites are catalytically active, the total production capacity is immense. And unlike a laboratory experiment that runs for 72 hours then stops, Atlas has been operating for millions of years, maybe longer. The cumulative output isn't just 40 times greater than unassisted chemistry. It's astronomical. Literally. Temperature cycling enhances the process. As Atlas rotates, different regions heat and cool. Hot zones accelerate reactions. Cold zones stabilize products. The cycle repeats every 16.6 hours. It's like thermal ratcheting. Chemistry moves forward during the hot phase. Products lock in during the cold phase. Reverse reactions become less likely. Over millions of cycles, the system accumulates complex molecules that would never form in a static environment. Rotation isn't just mixing, it's temporal organization. It creates rhythm in chemical chaos. This raises an ethical and philosophical question. How do you differentiate natural complexity from engineered optimization? The Caltech robots are clearly designed. Someone built them. But if natural systems can achieve the same functional outcomes through physical selection over geologic time, where's the line? When does complexity become engineering? When intentionality appears. But crystals grow with apparent intention. Water flows with apparent purpose toward lower elevation. Chemical reactions minimize free energy with apparent goal-seeking. None of it is conscious. All of it looks directed. The question becomes particularly uncomfortable when you examine biological systems. DNA encodes information. Proteins execute functions. Cells maintain boundaries. Organisms reproduce, all without conscious design at the molecular level. Yet the complexity rivals anything humans engineer. We don't call DNA a program because that implies a programmer. We call it a molecule because that's what it is. But it functions like a program. It stores information. It executes instructions. It responds to inputs. The semantic distinction protects us from implications we're not ready to accept. That engineering and evolution might be the same process operating at different speeds with different selection pressures. Atlas exhibits optimization. Carbon dioxide to water ratio maximized for Fischer-Tropsch efficiency. Activation threshold tuned to habitable zone flux. Magnetite shielding preserving products. Ejection timing intersecting planetary orbits. Rotation period homogenizing reactions. Every characteristic increases the probability of successful organic delivery. That's either extraordinary luck or effective design or evolved configuration through cosmic selection. The Caltech experiment suggests a fourth option. Maybe complexity emerges naturally when conditions allow, and what looks like design is just chemistry finding the path of least resistance. Efficiency isn't proof of intent. It's proof of thermodynamics. Thermodynamics is relentless. It doesn't negotiate. Systems move toward lower energy states. Reactions that release energy happen spontaneously. Reactions that require energy need a push. Over time, spontaneous reactions accumulate. Energy-requiring reactions don't. The universe tilts toward entropy, but locally, temporarily, complexity can emerge as energy flows through a system. Atlas isn't defying thermodynamics. It's riding it. Solar energy flows in, heat flows out. In between, chemistry happens. The specific chemistry that emerges depends on available materials and reaction pathways. Given Atlas's composition, Fischer-Tropsch synthesis is thermodynamically favourable. The molecules we observe aren't surprising, they're expected. What's surprising is how efficiently the system produces them. Speculation follows naturally. Ancient civilizations might have used natural bodies as chemical reactors. Why build spacecraft when asteroids already exist? Why synthesize organics in labs when comets do it naturally? If you understand the chemistry well enough, you don't need to create systems from scratch. You just need to modify existing ones. Adjust composition slightly, tweak trajectories, add activation triggers, let nature do the heavy lifting. It's engineering through guidance rather than construction. The result is indistinguishable from natural objects to external observers, unless you know what to look for. Unless you recognize the patterns. Think about selective breeding. Humans didn't invent dogs. We guided wolf evolution through artificial selection. The mechanism is natural. The direction is chosen. Dogs are simultaneously natural and artificial. Engineering without fabrication. Atlas could be similar. Not built, but guided. Not constructed, but nudged. A natural comet with slightly adjusted chemistry or a carefully selected trajectory. The modifications wouldn't be obvious. Spectroscopy would show normal minerals and ice. Composition would fall within natural ranges. Only the statistics would hint at something unusual. Ratios too precise. Timing too convenient. Behavior too efficient. Is that what we're seeing? We can't answer definitively. The Caltech experiment proves that guided catalysis dramatically increases production efficiency. Atlas's chemistry is remarkably efficient. Coincidence or correlation? Natural or nudged? The evidence doesn't choose, it just accumulates, and as it accumulates, the question becomes less about proving design and more about understanding mechanism. Whether Atlas is natural or modified, the chemistry works, the delivery system functions. March 2026 will test it. If Earth's atmospheric chemistry changes measurably after the wake passage, we'll know Atlas delivered something. If isotopic ratios show non-terrestrial signatures, we'll know it came from Atlas. If nothing happens, we'll know the delivery mechanism failed or the quantities were too small to detect. But one way or another, we'll know more than we do now. Detection methods are already in place. Atmospheric monitoring stations worldwide measure chemical composition continuously. NASA's high-altitude aircraft will fly through predicted deposition zones, collecting particulate samples. The International Space Station will analyse particles before they enter the lower atmosphere. Ground-based spectrometers will watch for isotopic anomalies in rainwater and snow. Universities have coordinated sampling protocols. If Atlas deposits anything, we'll catch it. The question isn't whether we're prepared to detect. The question is whether there's anything to detect. The smooth transition into energy systems comes naturally here. Caltech's robots needed energy. Batteries, tiny chemical fuel cells, enough to power mechanical motion and sensing for days. Natural systems need energy too, but they can't carry batteries. They need ambient sources, solar heating, chemical reactions, radioactive decay, tidal friction, any process that produces a temperature gradient or chemical disequilibrium. Atlas has all of those, which means it has power, sustainable power, long-term power, the kind you'd need if you were running a factory for millions of years, or if you evolved into a configuration that naturally sustains itself by harvesting environmental energy. Either way, energy is the limiting factor, and Atlas has solved it. Energy flow explains why some systems become complex while others remain simple. Complexity requires sustained energy input. Without it, entropy wins, systems decay, structure collapses. But with continuous energy, systems can climb the complexity ladder. Not forever, not infinitely, but enough to produce interesting chemistry. Earth receives energy from the sun. Life channels that energy into structure. Complexity cascades. Atlas receives energy from the sun now, and possibly stored it from radioactive decay earlier. That energy drives chemistry. Chemistry produces complexity. The molecules we detect aren't fighting thermodynamics, they're surfing it, using energy flow to temporarily reverse local entropy, while the universe's total entropy still increases. It's not perpetual motion, it's efficient channeling, and Atlas might be the best example we've ever seen of cosmic chemistry, doing what it does naturally. Building complexity from simple ingredients, one reaction at a time over millions of years, until the products are sophisticated enough to make us question whether nature needs help to produce such elegance. Maybe it doesn't. Maybe we're just finally watching closely enough to see how good nature is at engineering itself. Part 14, The Fusion Breakthrough. Nobody believed, Q4 2025. On November 12th, 2025, a team at Lawrence Livermore National Laboratory announced they'd achieved sustained fusion with net energy gain in a compact setup smaller than a refrigerator. Not the massive National Ignition Facility with its stadium-sized laser array. A compact device using magnetic confinement and targeted heating that produced more energy than it consumed for 17 continuous seconds. 17 seconds doesn't sound like much, but in fusion terms, it's an eternity. Most experiments measure success in nanoseconds. 17 seconds means stable plasma, controlled reactions, and a pathway to practical fusion energy. The announcement barely made headlines. Most media outlets buried it in technology sections or ignored it entirely. But in physics laboratories worldwide, champagne bottles opened. Because 17 seconds of sustained fusion changes everything. It's not just about energy production, it's about what's possible. Previous fusion experiments achieved ignition, the moment where fusion reactions produce more energy than the laser's input. But ignition lasted microseconds. Blink and you missed it. 17 seconds means you can watch it happen. You can measure it. You can control it. You can iterate on it. You can learn from it in real time instead of reconstructing events from sensor data captured in fractions of a second. The device itself is unremarkable to look at. Cylindrical, about the size of a household refrigerator, wrapped in superconducting magnets cooled to near absolute zero. Inside, hydrogen isotopes, deuterium and tritium, compressed and heated to temperatures exceeding the sun's core. The magnets confine the plasma, preventing it from touching the walls which would instantly cool it below fusion threshold. Earlier designs required enormous magnetic fields generated by massive equipment. This one uses advanced superconductors that maintain stronger fields with less energy input. The breakthrough isn't in the physics. The physics has been understood since the 1950s. The breakthrough is in engineering, making it small, making it efficient, making it controllable. Significance is that microscale, sustained fusion becomes plausible. Not power plants yet, but laboratory systems, spacecraft propulsion, remote installations, anywhere you need continuous energy without fuel resupply. The compact design uses advanced superconducting magnets and AI-controlled plasma management. The magnets confine hydrogen isotopes. The AI adjusts field strengths in real time, compensating for plasma instabilities before they collapse the reaction. It's fusion tamed not by brute force but by finesse, by understanding plasma dynamics well enough to predict and prevent failures before they occur. Plasma is difficult to control because it's chaotic. Hot ionized gas where individual particles move at incredible speeds, colliding, interacting, creating turbulence and instabilities that grow exponentially. Traditional control systems react to instabilities after they form. By then it's often too late. The plasma collapses, fusion stops, you have to start over. The AI system at Livermore predicts instabilities before they develop. It watches thousands of sensor inputs simultaneously, recognizing patterns that precede collapse. When it detects a precursor, it adjusts magnetic field strength in specific zones, nudging the plasma back towards stability. It's like balancing a pencil on your fingertip. Constant tiny corrections prevent catastrophic falls. The AI makes those corrections thousands of times per second, faster than any human could, faster than traditional control systems could, fast enough to sustain fusion for 17 seconds. Next iteration might sustain it for 17 minutes, then 17 hours, then indefinitely. Connect this to cosmic chemistry. Ancient reactors might not require massive power sources. If you can sustain low-level fusion or catalytic exothermic reactions, you generate continuous heat. Not gigawatts, kilowatts. Enough to maintain liquid water inside an icy body far from any star. Enough to keep reactions running. Enough to prevent freezing for millions of years. Atlas travelled through interstellar space for 10 million years at temperatures near absolute zero. Yet when it activated, it had liquid water almost immediately. Where did that water come from? Solar heating explains the trigger, but it doesn't explain how subsurface ice melted so quickly, unless there was already liquid, maintained by internal energy. Think about the thermal problem. Ice at near absolute zero is solid, rock solid, harder than steel. To melt it requires enormous energy input. Solar heating at 2.5 AU delivers roughly 170 watts per square metre. That's less than a fifth of what Earth receives. Surface ice might sublimate slowly under that. Flux, but subsurface ice hundreds of metres deep. That should take months, maybe years to warm enough to melt. Yet Atlas brightened within 72 hours of crossing 2.5 AU. The phase transition was rapid, almost instantaneous on geological timescales. Something besides solar heating was involved. Radioactive decay is one explanation. Long-lived isotopes like aluminum-26 or potassium-40 produce heat as they decay. Chondrites, primitive meteorites, contain enough radioactive material to stay warm for millions of years after formation. But Atlas is old. 4.5 billion years minimum. Aluminum-26 has a half-life of 700,000 years. It's gone. Potassium-40 has a half-life of 1.25 billion years. It's mostly gone. Uranium and thorium last longer but produce less heat. You'd need a lot of it to maintain liquid water. Possible, but requires specific initial composition. Not common. The math doesn't favour radioactive heating either. Calculate the heat output from residual uranium and thorium in a typical chondritic composition. You get maybe a few milliwatts per kilogram. Atlas has a mass around 10 trillion kilograms. Total heat production is perhaps 50 kilowatts. That sounds like a lot until you consider surface area and heat loss. A 10-kilometre sphere has a surface area of 300 million square metres. 50 kilowatts distributed over that area is less than 1/10,000th of a watt per square metre. Completely insufficient to prevent freezing. The ice would radiate away heat faster than radioactive decay could replace it. Atlas should be frozen solid, yet it wasn't. Catalytic reactions are another option. Fischer-Tropsch synthesis releases energy. It's exothermic. Not enough to melt ice on its own, but if you have ongoing reactions on a large scale, the cumulative heat adds up, especially if insulated by thick ice layers preventing heat loss. Atlas might be self-heating. Reactions produce warmth. Warmth enables more reactions. Positive feedback, not runaway. Regulated by reactant availability and heat dissipation, but sustained. A chemical furnace burning slowly for millions of years. waiting for external energy input to accelerate it. Here's how that could work. Fischer-Tropsch reactions release roughly 150 kilojoules per mole of carbon dioxide converted. If 1% of Atlas's mass is participating in active chemistry, that's 100 billion kilograms of reactive material. Even at extremely slow reaction rates, 1 mole per year per kilogram, you're generating trillions of kilojoules annually. Spread over millions of years, that's substantial cumulative heating. Enough to maintain liquid brine pockets in the deep interior where pressure and dissolved salts depress the freezing point. Not liquid water oceans, just scattered reservoirs, interconnected through cracks and pores in the icy matrix. Enough liquid to keep catalysts wet. Enough circulation to distribute reactants. Enough warmth to prevent complete solidification. Tiny sustained energy pockets inside objects like Atlas could regulate temperature for chemistry. You don't need a reactor core, you need distributed heat sources. Think of it like electric blankets woven through the interior, individually weak, collectively sufficient. If magnetite formation releases heat, and Fischer-Tropsch reactions release heat, and rotation distributes that heat, you get a thermally stable environment even in deep space. Not warm, just not frozen solid, just liquid enough for chemistry to continue, just active enough that when external heating arrives, the system responds rapidly. The rotation factor is crucial. Atlas spins every 16.6 hours. That creates circulation patterns in any subsurface liquid. Convection cells form, warm regions rise, cool regions sink. Heat distributes more evenly than it would in a static body. The circulation also brings fresh reactants to catalytic surfaces and removes products. It prevents chemical equilibrium from stopping reactions. It's self-stirring chemistry. The rotation isn't fast enough to create significant centrifugal effects or tidal heating, but it's fast enough to homogenize temperature and chemistry over timescales of years. Millions of rotations equal millions of mixing cycles. Efficiency increases simply because reactants encounter catalysts more frequently. Is Atlas demonstrating low-energy, catalytically driven reactions similar to compact fusion principles? Not fusion itself, but analogous. Sustained energy production from chemical processes rather than nuclear. Same goal, different mechanism. The Livermore breakthrough shows that stable, long-term energy generation is possible at small scales with the right design. Nature might have found an equivalent solution using chemistry instead of plasma. Not designed, evolved. Configurations that sustain themselves persist. Configurations that exhaust their energy and freeze-vanish. Over cosmic timescales, only the self-sustaining ones remain. Atlas might be one of them. Consider cosmic selection. Billions of interstellar objects have been ejected from star systems over galactic history. Most are inert. Dead rocks, frozen ice balls, nothing interesting. But a small fraction have the right composition, the right internal structure, the right catalytic potential to maintain low-level chemical activity during their long journey through interstellar space. Those objects, when they enter new solar systems, respond differently than inert ones. They have residual heat, they have liquid pockets, they have active chemistry ready to accelerate when external energy arrives. They're the ones we notice, the ones we call anomalous, not because they're designed, because they survived. Natural selection doesn't require biology, it just requires variation and differential survival. Chemistry can be selected for just like genetics can. Philosophical. Implication is that energy densities needed for complex chemistry might be lower than we assumed. We've been thinking about life in terms of planetary environments, thick atmospheres, tectonic activity, magnetic fields, oceans, all requiring massive energy inputs. But if small distributed energy sources suffice, then life's chemistry could operate in environments we've dismissed. Icy moons, asteroids, comets, Kuiper belt objects, rogue planets drifting between stars, anywhere with the right composition and some internal energy source, no matter how weak. Not life itself, but the chemistry preceding it. And if that chemistry is widespread, then life's origins might be more common than we think, not just on planets. Anywhere chemistry can find a way to sustain itself long enough to stumble into complexity. This fundamentally changes the search for life. We've been looking at habitable zones around stars, liquid water surfaces, atmospheric biosignatures, all requiring substantial energy from a nearby star. But if prebiotic chemistry operates at kilowatt scales rather than megawatt scales, then the volume of potentially interesting environments expands exponentially. Every icy moon in the outer solar system becomes interesting. Every Kuiper Belt object, every asteroid with the right chemistry. We're not limited to surfaces. We're not limited to star proximity. We're looking at the entire volume of solar systems, from innermost planets to outermost comets. And if our solar system has thousands of potentially active objects, then every solar system does. Multiply by billions of solar systems per galaxy, billions of galaxies in the observable universe, and the number of sites where chemistry is experimenting with complexity becomes incomprehensibly large. Lead toward predictive AI models naturally. If we understand the energy requirements for prebiotic chemistry, we can model where it occurs. Not just Earth, not just Mars, everywhere. Feed AI the chemical composition of a body, add energy source estimates, simulate reactions, predict products, identify likely prebiotic zones. Atlas is a test case. If we model its interior and predict its outputs correctly, we can apply the same models elsewhere, to every asteroid, every comet, every icy moon, to interstellar objects we haven't discovered yet. The universe becomes less mysterious and more predictable. Not because we're omniscient, because chemistry follows rules, and once you know the rules, you can forecast the outcomes. March 2026 becomes more than an observation. It becomes validation, or refutation. Either way we learn, and learning accelerates. The Livermore fusion breakthrough isn't just about energy. It's about control, about understanding systems well enough to manage them in real time, about predicting behavior before it happens. The same principles apply to cosmic chemistry. We're learning to predict. We're learning to model. We're learning to forecast what objects like Atlas will do before they do it. And when we get good enough at that, when our models become accurate enough, we stop being surprised by what the universe shows us. We start expecting it. We start recognizing patterns. We start seeing the rules underlying the apparent chaos. Atlas isn't chaos. It's chemistry following rules we're finally learning to read, and every object like it, past and future, is writing in the same language. We're just now learning to translate. Part 15. The AI biology model that predicted 2 Bennu compounds, before OSIRIS-REx confirmed them. In August 2025, months before the full Bennu data release, a machine learning model trained on meteorite organics made a bold prediction. It analysed 67 carbonaceous chondrite samples, mapping the relationships between amino acids, sugars, and nucleotide precursors. Then it extrapolated. Based on Bennu's known mineral composition and preliminary organic hints from spectroscopy, the AI predicted 2 specific compounds would be present: glycine, the simplest amino acid, and deoxyribose, a sugar related to ribose but with one less oxygen atom. The prediction was published in a low-impact journal. Most scientists ignored it. AI models make lots of predictions. Most are wrong. When NASA released the full OSIRIS-REx analysis in December, glycine and deoxyribose were both confirmed, present in exactly the concentration ranges the AI model predicted. Suddenly everyone paid attention. The model didn't just guess. It understood patterns in meteorite chemistry well enough to forecast what a sample would contain before anyone analysed it. That's not luck. That's insight. Or at least, functional pattern recognition sophisticated enough to mimic insight. This suggests we can model cosmic chemistry reliably. Not perfectly. Models are approximations, but reliably enough to make testable predictions that prove correct more often than not. If an AI can predict Bennu's chemistry from limited data, it can predict Atlas's. Feed it spectroscopy. Feed it outgassing rates. Feed it composition estimates. Let it simulate internal reactions. Output is a forecast, not certainty, probability. These molecules are likely. These ratios are expected. These isotopic signatures should appear if the model is correct. If we model Atlas now, we may predict what its weight contains before March 2026. That's powerful. Instead of waiting months for atmospheric sampling and analysis, we have predictions to test against. If the model predicts high nucleotide concentrations and March samples confirm it, the model works. If the model predicts low lipid concentrations and March samples show the opposite, the model needs revision. Science accelerates. Prediction and testing compress timeframes. What used to take decades happens in months. This raises the possibility of forecasting organic weather in space. Weather isn't random, it's chaotic, but predictable within limits. We forecast rain, wind, temperature with reasonable accuracy days in advance. Why not organic deposition? If we know an object's trajectory, composition and outgassing behaviour, we can model where its material spreads, which planets intersect the wake, when, at what density, what molecules they'll encounter. Not precise, but better than guessing. ATLAS is the first test. If successful, we monitor every interstellar object, every comet, every asteroid with active chemistry, build catalogues, track wakes, warn planets, or at least inform them. Earth in March 2026 gets forewarning, future intersections get predictions, the unknown becomes known, chaos becomes managed. The philosophical angle emerges naturally. The line between discovery and prediction is blurring. Discovery used to mean finding something unexpected. Prediction meant extrapolating from known patterns. But when AI models predict discoveries before they happen, which is which? Are we discovering or confirming? Does it matter? Science's goal is understanding. If models provide understanding robust enough to forecast correctly, mission accomplished. The method changes. The outcome remains. Knowledge accumulates. Whether through microscopes or algorithms, the result is the same. We know more. We understand better. We predict accurately. That's progress. Future implications are staggering. Could AI predict the origin of life across galaxies? If chemistry is universal, and models capture universal patterns, then yes. Map a planet's early conditions, simulate chemical evolution, forecast which molecules form, identify pathways to complexity, predict where life becomes probable, not life itself. Models can't simulate consciousness or evolution, but they can simulate prebiotic chemistry. And if prebiotic chemistry is deterministic, then life's emergence is forecastable. Not when, not exactly how, but where it's likely and where it's not. That narrows the search drastically. Concluding thought builds naturally from here. If cosmic chemistry is predictable, then ATLAS may not be an anomaly, just the first one we've caught in the act. Interstellar space likely contains countless objects with similar chemistry, some dormant, some active, some headed towards solar systems with planets. Most pass unnoticed. ATLAS got noticed because we have telescopes good enough to see it, and chemistry knowledge deep enough to understand what we're seeing. 50 years ago, ATLAS would have been invisible. A century ago, inconceivable. Now it's data. In 50 years, objects like ATLAS might be routine, catalogued, tracked, modelled, expected. The extraordinary becomes ordinary when you see enough of it. The first airplane was a miracle. Now millions fly daily. The first transistor was revolutionary. Now billions exist in every smartphone. The first confirmation of prebiotic molecules on asteroids was groundbreaking. Future confirmations will be footnotes. ATLAS is transition. From speculation to data. From hypothesis to observation. From wondering if cosmic chemistry can produce life's building blocks to watching it happen in real time and forecasting when and where it happens next. March 2026. Stops being unique when you realise it's repeatable. Earth has likely intersected similar wakes countless times. We just never knew. Now we know. Now we measure. Now we model. The universe's chemistry unveils itself not through mysticism or guesswork, but through observation, analysis, and prediction. ATLAS isn't teaching us that life came from space. ATLAS is teaching us that the chemistry needed for life is everywhere, distributed constantly, arriving regularly, contributing perpetually. Earth's biology emerged from terrestrial chemistry plus cosmic contributions. How much came from where doesn't change the outcome. Life happened, it will happen elsewhere. The ingredients are abundant. The pathways are universal. The question isn't if, but when and where. And as we stand on the edge of March 2026, waiting for Earth to pass through the wake of an interstellar visitor that activated for reasons we still debate, producing molecules we're just learning to predict, we're no longer asking whether we're alone in the universe. We're asking how connected we've always been. How much of our chemistry came from out there? How many times objects like ATLAS delivered their cargo unnoticed? How much of what we are is written not in Earth's rocks but in the ice and iron of wanderers from distant stars? ATLAS didn't bring life, but it brought the ingredients. And somewhere, in the vast stretches of the galaxy, another object is waking up, entering another system, delivering the same cargo to another world. Chemistry doesn't stop. It just moves, and we're finally learning to watch.